Okay, welcome to this afternoon's information theory session. We are going to start with Koji Yamaguchi on quantum geometric tensor determines the i.i.d conversion rate in resource theory of asymmetry for any compact Lie group.
Thank you very much for the introduction. I'm Koji Yamaguchi from the University of Electrocommunications. And today, I'm going to tell you about our recent work on the resource theory of asymmetry, where we established the i.i.d conversion theory for any continuous symmetry described by a compact Lie group. And this is the joint work with Yosuke Mitsuhashi, Tomohiro Shitara, and Hiroyasu Tajima. And all the detail of the result can be found in the paper on arXiv. So let's get started. The resource theory of asymmetry is a theoretical framework to investigate the symmetry and its breaking from the viewpoint of quantum resource theory. And one of the central problems in any resource theory is a resource manipulation theory. A standard setup is an i.i.d asymptotic setup where we convert copies of a state into i.i.d copies of another state with an asymptotically vanishing error. And for example, in Fermat's entanglement theory, the conversion rate among pure states is given by the ratio of the entanglement entropy. So this property makes the entanglement entropy special amongst other entanglement measures. And in the resource theory of asymmetry, pure state conversion theory has not been fully established so far. And even for the simplest Lie group, U1 group, the pure state conversion theory has been completed very recently. And for other groups, not many is known. And for example, for SU2 group, the conversion rate is calculated for a restricted set of pure states. And even if we restrict our attention to reversible conversion, there is a conjecture called Marbian-Speckens conjecture, which is expected to provide a necessary and sufficient condition for reversible conversion. But this conjecture has remained unsolved for a decade. So given these situations, a natural question we should ask is what is an asymmetry measure that determines the conversion rate in the resource theory of asymmetry? And our study shows that the answer is quantum geometric tensor. And by using a formula for conversion rate calculating to calculate the conversion rate with the quantum geometric tensor, we will get a unified understanding of the prior studies on the asymptotic conversion rate in the resource theory of asymmetry. And in addition, we affirmatively proved the Marbian-Speckens conjecture. So these are the list of what we're going to see in the rest of my talk. So let's get started. In order to explain our result, let me first provide the definition of the resource theory of asymmetry. Any quantum resource theory is characterized by specifying the free states and free operations which are assumed to be easily prepared and easily implemented. And in the resource theory of asymmetry, free states are symmetric states, and free operations are G covariant operations. Here, we say that a state law is symmetric if and only if the state is invariant under any group transformations. Here, capital G is the group describing the symmetry of interest, and UG describes the evolution, the group transformation, where U is a projective interrepresentation of G. On the other hand, a G covariant channel is defined as follows. A quantum channel E is called G covariant if and only if it commutes with the group transformation. Here, in general, the input system and the output system of the quantum channel can be different from each other. So in general, we have two different unitary representations for those systems. A simplest example of a G covariant operation is G invariant unitary evolution, where the unit operator V describing the evolution is commute with all the unitary representations. And in general, the Stein-Spring dilation theorem provides a physical interpretation of the G covariance. Here, which states, the theorem states that quantum channel is G covariant if and only if it is described by this quantum circuit, where the unitary evolution is assumed to be G invariant, and the initial state of the unshared system is assumed to be symmetric. So in this way, in this sense, we can say that the G covariant channel describes a general time evolution under the conservation law without introducing any asymmetry from external systems. So these two tools, these two notions, I mean the symmetric states and the G covariant operations, defines the resource theory of asymmetry. Okay, in order to explain our result properly, let me introduce few terminology and notations. The central quantity we're going to investigate is optimal conversion rate. We say that a state law is approximately asymptotically convertible to another state sigma with a rate R if there exists a sequence of a G covariant channel which maps i.i.d. copies of state law to our i.i.d. copies of sigma with a vanishing error. Here we adopted the trace distance as a quantifier of error. And if this condition is satisfied, we say that rate R is achievable. And the supremum of achievable, such an achievable conversion rate is denoted by R. And the main focus of this study is to calculate the conversion rate between two pure states, psi and phi. There is a simple but important characteristic of the symmetry of a state, which is called the symmetry subgroup. The symmetry subgroup of a state law is defined as the group element whose group transformation leaves the state invariant. And for example, a state law is symmetric if and only if the symmetry subgroup itself is equal to the group itself. Sorry. And relatively easily, we can prove that the symmetry subgroup provides a necessary condition for the conversion rate to be non-vanishing. Intuitively, this is because that under the G covariant under the conversion using the G covariant operation, the state becomes less asymmetric or equivalently more symmetric. So for the conversion to be possible, the symmetry subgroup should be enlarged when compared between the initial state and the final state. So this is the intuition behind of this fact. And finally, let us introduce the notion of let me explain the notion of quantum geometric tensor. The quantum geometric tensor is a local geometric characteristic of a family of pure states parameterized by a lambda, real parameter lambda. And if there is m independent parameters, the quantum geometric tensor is a square Hermitian matrix of order m defined by this equation. And in the resource theory of asymmetry, quantum geometric tensor can be introduced by using a projective unitary representation of a Lie group G. And for this purpose, we fix a basis of a Lie algebra to parameterize the group element near the identity in this way. And then with projective unitary representation of U, we can introduce a parametric family of pure states. And by using the Hermitian operators defined by differentiating the unitary representation, we can obtain the quantum geometric tensor, which we will denote QIP psi. And this is shown to be equal to the non-symmetrized covariance matrix for these operators. In our study, we show that the quantum geometric tensor is a valid asymmetry monotone in the sense that if psi is convertible to phi without error by using G covariant channel, then this inequality holds as a matrix inequality. So by using these notations, we can now state our main theorem. When we consider a conversion, asymptotic conversion from psi, pure state psi, to another pure state phi, our theorem states that the conversion rate is given by this equation. As I mentioned, that the inclusion relation between the symmetry subgroup does not hold the conversion rate is becomes 0. But if the inclusion relation is satisfied, then the quantum geometric tensor determines the conversion rate. Here, Gi is a representative element of each connected component of G. And so in particular, if G is connected, there is only one connected component, implying that the formula it can be written as a single by using a single matrix inequality. And importantly, since a compact Lie group has a finite number of connected components, this formula includes only a finite number of matrix inequality. So in this sense, this rate is indeed computable. Now let us compare our result with the prior researches. As I mentioned, there were several prior researches on the conversion rate for different setups, but I think all of these results look different from each other. But as we shall see soon, our single formula can provide all of these results. Okay, let's start with the example of U1 group, which is the simplest Lie group. And we consider unitary representations of U1 group given by these equations, where H and H prime can be interpreted as Hamiltonians. And for U1 group, since the dimension of the Lie group is 1, the quantum geometric tensors are simply scalars, and given by it is shown to be equal to the variance. So by using our formula, we can calculate the conversion rate given by the ratio between the variances. And this result reproduces prior research on the time translation symmetry, where the conversion rate is calculated among pure states having the same period. And importantly, the assumption on the period in the prior research is now mapped to the assumption on the symmetry subgroups. Okay, so this is the U1 result. And the result of the U1 theory is a simplest example of the reversible conversion. Here we say that two pure states, psi and phi, are asymptotically reversibly convertible if the product of the conversion rate in both directions is equal to 1. And by using our formula, we can derive a necessary and sufficient condition for the conversion to become reversible. And for simplicity, let us consider the case of a compact connected Lie group where we only have one matrix inequality. And from this formula, we can see that the conversion is reversible if and only if two conditions A and B are satisfied, where A is a condition on the symmetry subgroup, while the B is a condition about the quantum geometric tensor. And I would like to remark that there is a conjecture called Marbian-Speckens conjecture on the same setup, where the conversion rate is where it is conjectured that the conversion rate is reversible if and only if these three conditions are satisfied. The first condition is nothing but the condition A in uniform relation. And the second condition is about the proportionality between the symmetrized covariance matrix. And the third condition is about the condition on the expectation value for operators in a commutator subalgebra. And as I mentioned, the condition A is nothing but the condition 1 in the Marbian-Speckens conjecture, while the condition B about the quantum geometric tensor, the symmetric and anti-symmetric part of this equality between the quantum geometric tensor corresponds to the condition 2 and 3 in the Marbian-Speckens conjecture, respectively. So in this way, as a bonus, by using our formula, we have affirmatively proven the Marbian-Speckens conjecture, which has remained unproven for a decade. So since we have now obtained a necessary and sufficient condition for reversible conversion, we can find example where the conversion becomes irreversible. And for example, the condition B is an equality between the matrix. So this condition can be easily violated. So as a simple example, we consider a SU2 group. And although our formula is applicable to any pure state, for simplicity, we confined ourselves to a subspace spanned by a highest weight state. And under this assumption, quantum geometric tensor is shown to be parameterized by using two parameters m and v, where m is mean for this operator j, and v is variance for this operator j. And so from this expression, by using our formula, we can calculate the conversion rate given by this equation. And again, this result reproduces the result in the prior researches, where the conversion rate for pure states are calculated for the same subspace. Okay, so finally, let me comment on the finite group. Although a finite group itself is not a Lie group, we can calculate the conversion rate by appending a trivial phase. And in order to explain more, we fix a projective unit representation of finite group U and U prime, and we append a trivial U1 phase and define U tilde and U tilde prime, which is the representation of G tilde. And importantly, a trivial phase does not affect the convertibility. And also, it does not affect the inclusion relation of the symmetry subgroup. And since G tilde is now a compact Lie group, we can apply our formula. And the quantum geometric tensor vanishes for, we can show that the quantum geometric tensor vanishes for any pure state, implying that this matrix inequality holds for any R. So by using this fact, we can show, we find that the conversion rate is either infinity or 0, depending on the inclusion relation between the symmetry subgroups. And again, this reproduces a result in the prior researches for finite group. So our formula can be applicable is applicable not only for continuous symmetry, but also discrete symmetries. Okay, so far we have seen that our formula reproduces reproduces a result in the prior researches, and so now I will explain a very rough sketch of the proof strategy. And the proof, thank you very much. The proof of our formula consists of converse and direct part. Here, in the converse part, we show an upper bound of achievable rate, while in the direct part, we show the achievability of that bound. And in order to show in the proof of converse part, we first connect the quantum geometric tensor to a Pelt's monotone metric, and it can be shown that the QGT is obtained as a limit of Pelt's monotone metric. And by using the monotonicity of this metric and by investigating its asymptotic behavior, we can show that the quantum geometric tensor is an asymmetric monotone and asymptotic conversion. And by using this monotonicity, we can prove the upper bound. We can prove an upper bound on the achievable conversion rate. And in the proof of direct part, we use a dual formulation of the convertibility. So far, we have considered a conversion from a state psi to another state phi by using a G covariant channel. And here we now consider another setup where we convert a family of state to another family of state by using a quantum channel, which is not assumed to be G covariant. And if we regard this G as an unknown parameter, this is a conversion between statistical models. And it can be shown that these two conditions are equivalent to each other. And importantly, the asymptotic behavior of i.i.d. copies of statistical model was investigated in the context of quantum local asymptotic normality. And by using the result inspired by this study, where the conversion channel are explicitly constructed in our study. But I did not explain the detail here. So here's a summary of my talk. We have established the pure state i.i.d. conversion theory in the research theory of asymmetry for continuous symmetry described by any compact Lie group. And the conversion rate is given by this formula, where it is calculated by using the quantum geometric tensor. And importantly, again, there is only a finite number of matrix inequalities, so it's indeed a computable rate. And this formula provides a unified understanding of prior studies on asymptotic conversion rate in the resource theory asymmetry for different setups, including not only the continuous symmetry, but also the discrete symmetries. And in addition, we have affirmatively proved the Mabian-Speckian conjecture on reversible conversion. OK, that's all. Thank you very much.
Thank you very much. So the perfect place to resolve this conjecture. Do we have any questions?
Hey, thanks for the nice talk. So let's say you take two states for which the rate of conversion is like 0. You cannot go because the symmetry group, they don't obey this inclusion relation. Can you at least produce, like, let's say, one single copy of the second one from arbitrarily many copies of the first one with asymptotically vanishing error? Because I seem to remember in Iman's paper you could do that somehow, even if the rate was 0.
Well, I don't think so. I think if the inclusion relation is not satisfied, the conversion rate is always 0.
Yeah, the rate, yes, but can you produce one output copy with very good error?
Well, I don't think it's possible, but yeah, I think it is impossible. Yeah.
All right, thanks.
Yeah, great talk. I know this is usually hard, but do you have some conditions where you can say something on the number of copies you actually need?
Sorry, could you?
Can you say something about the number of copies you need for this conversion? N. How large do you have? Maybe in some cases, or there's some assumptions, at least an idea how large the N is?
Do you mean the
N
for a
in your
given, for
definition,
example,
right?
threshold for the error? Can we
You
find
have
that?
your R, and you say that for large enough N, something happens. I understand that correctly, right? How large does the N have to be?
Well, we haven't carefully analyzed, but as we have explicitly constructed the channels, so we can investigate the behavior of the rate, the error rate, and the number of copies, I think.
Thank you.
I do not have a cool.
I mean, if you can, it's certainly helpful or useful to know that eventually.
Yes. Thank you very much for the comment.
Time for maybe one last question.
Thank you for the great talk. My question is, why we need compactness of a Lie group?
Oh, that's a very good question. In fact, I think the converse part is valid even for non-compact Lie group. But in the direct part where we construct a quantum channel, we first estimate the parameter G. So here, G is the group element. And in that estimation process, if the if a group is non-compact, there is a difficulty coming from that. And there are several difficulties, but I think that's one of the critical points. We cannot estimate properly. We cannot estimate G properly if the group is non-compact.
Okay, thank you.
Yeah, maybe one more.
Thank you very much.
First, congratulations on the great result. Awesome. Just one quick question. What is known about mixed state? Because in the case of U1, we know that the rate is also given by SLD Fisher information in the case of mixed state.
Yes. In fact, in the version 2 of the paper, which we updated in the last week, we have some analysis on the analysis on the mixed state, and we have found upper bound for the distributive coherence, for example. And by using this formula, by using this result, one of your result on the impossibility on the distributed coherence can be reproduced. So we can extend. We do not have a comprehensive theory, but we have some result with which we can reproduce your result.
Great, thank you.
Thank you.
Let's thank the speaker again.
Thank you very much.